so there are these two aspects of gauge gravity duality. One is to find a theory of quantum gravity and a theory of everything. But on the other hand, because the gauge gravity duality involves strongly coupled theories, you can also use this as a method and in the more applied context of finding applications to strongly coupled systems. And and there's this interesting relation between these very fundamental and these very applied aspects. And today I would like to talk more about these applications. And so the first hour, I'm going to talk about some examples for applications to condensed matter physics. And the second hour, applications to quantum information. So I should say, so I've been very well, so I moved to Würzburg in 2016, and actually, so 1 year after the book appeared. And so in Würzburg, there's a very big condensed matter physics community. And so it was kind of natural to get involved there and actually start collaborations with my colleagues. And that worked actually very successfully. And I think maybe it's also interesting from a sociological point of view, so that we now have these joint projects between gauge gravity duality and condensed matter physics. And so I would like to show some of this to you. So I'm really going to focus on some really new research that we did in the past years. And so hope to explain to you what is interesting about this. Okay, so let me see if I can go full screen.
Yes. Yes, we can see the.
Okay, now let me try again. I always have to do it twice for some reason. No, okay, now it should work. Okay, so yesterday I told you about generalizations of ADS-CFT to systems in particle physics. And so first I told you about these meson masses that I've been involved in for some time ago. And so then I gave you this other very famous example due to these authors here, Kovtun-Son and Steinmetz, which really started all these applications to the real world. And so there's this shear viscosity, which is a transport coefficient. And I didn't mention this so explicitly yesterday, but so this is, of course, a coefficient that arises in the context of hydrodynamics. Okay. And so here we use some generalized definition of hydrodynamics, where it's an effective field theory of very long wavelength fluctuations. So you imagine you have a flow of some fluid, and then you don't have big wiggles, but you have some very soft kind of fluctuations that happen, and this can be described in the context of hydrodynamics. And so this shear viscosity is a friction term that appears in this context. And so yesterday I showed you that this has been very successfully applied to the quark-gluon plasma, which is a state of matter of QCD matter, quarks and gluons, that arises at finite temperature, and it's, for instance, investigated at this RIG accelerator, but also at CERN in so-called ALICE experiment. So in the context of heavy ion collisions, so you collide very heavy nuclei, and then they form this new state of matter called the quark-gluon plasma. And so in this quark-gluon plasma, actually, this shear viscosity over entropy density has been measured. And actually the result agrees very well with this prediction of gauge gravity duality, which is due to this universality of this result, because I mean, it really doesn't depend very much on the details of the theory. Okay, so this is one recurring theme in everything I'm saying. So ADS-CFT is always very powerful if you have a situation where the physics doesn't very much depend on the microscopic degrees of freedom, which is called universality. Okay, and of course, the fact that this works so well also seems to imply that actually the quark-gluon plasma is really a fluid, and so hydrodynamics is appropriate for describing this strongly coupled plasma. Okay, so this was a very big breakthrough because we start with these methods of string theory, quantum gravity, and then via the gauge gravity duality, we arrive at hydrodynamics as applicable to the quark-gluon plasma, and this has been checked in experiments successfully. So I think that's also a very interesting fact that we can start with string theory and arrive at something that can be measured in the lab, although it's of course somewhat indirect. Okay. And then, of course, this triggered lots of ideas if this can also be applied to other branches of physics. Okay. And so today I'm going to talk about further applications now in the context of condensed matter physics, where one looks at hydrodynamics also applied to electrons in solids. Okay. So now, of course, in the quark-gluon plasma, it's kind of natural to view this as a fluid, okay, because it's just some, some blob of matter that you have. But of course, if you have a solid in condensed matter physics, this means you have a lattice made out of ions, okay, or atoms. And then the electrons, of course, they move through, there's this band theory that is usually used, and the electrons move through this lattice. But of course, it's not really like having a bucket of water in which you can say, well, a pipe through which water flies, and you say, I apply hydrodynamics, because there's this issue that, of course, the electrons can scatter off these atoms and ions that form the lattice. And of course, if the scattering is the dominant effect, then you cannot really describe the electrons as being a fluid. And so you have to find a correct parameter window where this actually makes sense. And this is what I'm going to discuss to some extent also in the lecture today. So, and what we did was to investigate applications and generalizations of ADS-CFT also in this context of applying hydrodynamics to electrons in solids. Okay, so I should say a little bit about our funding because that's also so interesting in this context. So the CTQMAT is a big research initiative of condensed matter physicists that is funded in the so-called Excellence Initiative of the German federal government. And so I don't know if you know about science funding in Germany, but normally science funding is done by the Länder, so the different states. So Germany is divided into states like America, probably also Italy. And it's these states that are responsible for education and science in Germany. And so the federal government normally doesn't interfere very much. But here now this is very special because now they invented this program by which also the federal government gives money for big research initiatives, which are called excellence clusters. Okay, and so the CTQMAT is one excellence cluster which involves Würzburg and also Dresden. So it's really a big joint initiative in condensed matter physics. And so it's very interesting to note that our ADS-CFT projects are actually also funded within this program. And similarly, this SFB 1170, this is a Würzburg research initiative in condensed matter physics that is also funded. There's a big research collaboration here also locally in Würzburg on similar topics. And so we are very proud that us, the ADS-CFT physicists, are actually funded within this initiative as well. Okay, so as I said, I would like to show you a successful example where us, the people working in ADS-CFT and generalizations, have actually teamed up with some colleagues in our department who are true condensed matter physicists. And we managed to write a very nice paper together, which is called Turbulent Hydrodynamics in Strongly Correlated Cargo metals. Okay, I explain what a cargo metal is. Strongly correlated, you already guessed, because ADS-CFT is very good for strongly coupled systems. So this is also playing a role here. And let me just introduce our team here. So there's our colleague Domenico Di Sante, who is actually going to be a professor in Bologna from, I think, from October or so. So he will be very close to Urbino, actually. And so Martin Greiter is also a colleague here in Würzburg from condensed matter physics, and Ioannis Matayakakis, René Meyer, and David Rodriguez Fernandez, they are all working in ADS-CFT, so they are part of our ADS-CFT team. And Ronny Tomale is my colleague in condensed matter physics, professor for condensed matter physics, and Erik van Loon and Tim Wehling, they are at Bremen University, and they performed some particular calculations in condensed matter physics that we needed for this paper. So it's really a nice collaboration of people from very different backgrounds. So although everything is physics, of course, this is really an interdisciplinary project. And so we are very happy that this actually worked out. Okay, so what is happening in this paper? In this paper, we propose a new material, and this is a so-called Dirac material. I will explain to you also what a Dirac material is. So where this is a particular material where there is a quasi-relativistic dispersion relation for the electrons. And of course, ADS-CFT works well mostly for relativistic theories. And so then if we want to apply it to electrons in solids, we should at least make sure that the dispersion relation for the electrons looks like as if they were relativistic. I will explain this more later. Okay, so but this is a kind of prerequisite to be able to say something useful using ADS-CFT. And then also we want, as I explained already before, our results are best if the coupling is almost infinite. And so we require a rather strong coupling of these electrons, and even stronger than in graphene. So I'm sure you have heard of graphene, which are these hexagonal carbon sheets, and so which are very pure. And so far, this is the prototypical material for describing electrons by hydrodynamics in solid state physics. But now in this paper, we propose a new material, which has a quite peculiar name. So it's called scandium Herbert-Smithite. So Herbert Smith was an American mineralogist and crystallographer, and he discovered a particular material that was named after him. So it's called Herbert-Smithite. And so now we propose to substitute some atoms in this material which were actually zinc atoms, by so-called scandium atoms. And so then this material will be called scandium Herbert-Smithite. And so we propose this. So I should say this material doesn't exist yet. I mean, nobody has made this material yet, but I think it should be possible to try to actually make this in the laboratory. And so the reason we propose this material is to have an enhanced hydrodynamic behavior of the electrons, reaching smaller values of this shear viscosity over entropy density ratio that I showed to you. Okay. I think what I would like to do is just to briefly show you the front page of this paper. Okay. Sorry, why? No, I can't escape the. Okay, sorry. Oops. One more time. Yeah, okay, so now you can see this paper. Sorry, it always takes a long time to shift from one to the other. Okay, here now you can see it. Okay, so this is a paper published in Nature Communications, which is a rather famous journal, and certainly not the typical journal that people working in ADS-CFT will publish in. So it's a rather upscale journal and very famous. So we are very proud that we managed to end up in this famous journal. And so then here again you see this collaboration between condensed matter physicists and us, the gauge gravity duality physicist. Okay, let me just show you briefly. So how this looks like, and I will explain some of these figures to you now that are given in this paper as a nice example of using ADS-CFT also in this very applied context. Now I have to switch back to the, come on, sorry. Sorry, I have to go back to my slides. No, okay, sorry. Okay, so for the quark-gluon plasma, it's quite straightforward to write down a hydrodynamic theory for this quark-gluon plasma. But for electrons, in solids, it's more complicated because they're not there alone by themselves. Okay, so there's all these other things like the lattice, which is made out, so this metal is made out of a lattice. And so then what one has to ensure is that the electron-electron interactions are the strongest in this particular system that we are considering. And so when the phonon, so this is the interactions with the lattice vibrations, and of course in such a lattice there are always impurities also. So if they are suppressed, so we have a very clean material and we are in a particular region of temperature and density such that these electron-electron interactions are the strongest, then actually these electrons, they can be considered as forming a hydrodynamic flow. So they have this collective movement through the solid. And so that's, of course, a very interesting phenomenon. And also it's very useful for technology, because if there's this collective flow, then the resistance is supposed to be smaller than without hydrodynamic flow. Okay, the problem here is, of course, that this is possible only in a very small parameter window. And in particular, the electron interaction scale must be shorter than scales for interactions with phonos, impurities, or walls. So it really the shortest scale is the interactions between different electrons. Okay, so that's L is the typical scale for this, and this has to be the shortest, and that's the dominant one. Okay. Okay. Now this has been already investigated experimentally some time ago, where people looked at some wire, okay, made out of the solid, and studied the behavior of electrons moving in this wire. And so there were some results already some time ago in the context of weakly coupled semiconductors like this gallium arsenide. So Professor Molenkamp is also one of my colleagues here in Würzburg, famous experimentalist in condensed matter physics. And so there's some hallmark signal which I will show on the next slide. So there's a decrease of the so-called differential resistance, so the change of the voltage with the current when increasing the current that we apply. So I will show a picture of this in the next slide. And then there have been lots of investigations of hydrodynamic behavior of electrons in graphene, where the coupling is very strong. And then so this is very useful for obtaining this regime. And then people actually observe that, you know, the electrons, they start making kind of vortices or so, that which means that locally the resistance actually becomes negative, okay, which we wouldn't expect if the electrons all move in the same direction. And this is also seen as an example of a hydrodynamic behavior. Okay, let me give you some slightly more details about this. So how do we see that electrons in a wire behave like a fluid? Okay, so well, first we look at the wire. So these black lines are the wire in which we have our material. And so this wire should have a width which is called W. Now, if we are not in the hydrodynamic regime, we are in the regime where the collisions between the electrons and the atoms and the electrons and the walls of this channel dominate. This is the so-called Knudsen flow regime. Okay, so this is when the electron interaction scale as a function of the temperature is much bigger than the width of this channel. Well, then these electrons, they move through the channel and they just hit the walls. Okay, and so so this is the so-called collision-dominated regime. And so this fact that the electrons hit the walls and so on, this increases. So this forms the resistivity of the material. The electric resistance is because the electrons don't move ideally. And so from this paper here, this is the theoretical calculation of this, and this is the experiment. So let me explain what you see. So here they plot the current. Okay, I is the current in microampere. So there's a reflection symmetry here, so we can start at 0 and look at what happens in this direction. And here we have this differential resistance in ohm. Okay, so the change of the voltage with the current. So now in this regime where the electrons hit the walls, it means that if you increase the current that moves through the wire in this direction, well, the faster they move, the more they hit things, and then the resistance goes up here, okay, if you increase the current. But then actually at some point when the current becomes really big, the system moves to another regime, which is the so-called Poiseuille flow regime. So Poiseuille is a famous French physicist from the 18th century who discussed flows of hydrodynamic flows. And so already in the 18th century, he found this regime, which now we realize here in a quantum behavior. So so now if the strongest interaction is between the different electrons that move in this wire, and we have electron-electron collisions, then we actually have this, and this becomes dominant, and the electrons are less likely to hit the walls or impurities. So, and they have this collective behavior, and you can just think of all the electrons moving at once, essentially through this wire. And so there's a crossover to a different regime. So that was predicted by a theorist already in 1968, which is the so-called Gaugy effect. It's the crossover from this ballistic to this hydrodynamic regime. Okay. And if we are in this hydrodynamic regime, then the opposite behavior happens. So if you further increase the current, then the resistance goes down again. Okay, so because of this collective motion, there's less scattering of impurities in the walls, and then the resistance decreases. Okay, which is of course also technologically very interesting. And so this was the theoretical prediction of the crossover between these two regimes, and this has actually been really measured in the lab already quite some time ago now. So it is actually possible to describe electrons by hydrodynamics in such a flow. Okay, so as I said, the dominant, so the scale that tells us whether we are actually in this hydrodynamic regime. So there's only this very small parameter window. This is this length scale called LEE. So this is the scattering length for the electrons. And you can show that this electron length is inversely proportional to the effective coupling strength between the electrons squared. And this effective electron coupling strength is given by the elementary electronic charge. But then, so there's this permeability here, and well, this is h bar, and the Fermi velocity. Okay, so the Fermi velocity is the velocity at the Fermi surface, which is a very typical quantity considered in condensed matter physics. But then we just see that if this coupling becomes bigger, then the scattering lengths become smaller, and then obviously if the scattering lengths become smaller, this is the most dominant effect. And then we are more likely to have hydrodynamic behavior in our system. Okay, so so this is what we are after. To see better hydrodynamics, we need to increase this coupling strength. Okay. So are there any questions so far of what I'm doing?
Sorry, can you show a moment of the preceding slide and saying yes in x-axis what is one micro
Ampere, yeah.
Yes, which quantity is on the x-axis here?
This is the current of the electrons that flow here. So to make the electrons flow, you apply an electric field, okay? And then if there's an electric field, the electrons are pulled in this direction.
So in the x-axis there is the current, and the y-axis there is the velocity.
There's the resistance.
There is the resistance. Okay.
Yeah. Okay. So okay, very good. So we apply an electric field which makes the electrons in principle move in this horizontal direction.
Mm-hmm.
And then if the electrons move in this direction, then there's a current, and this current is I. And the larger the electric field, so the current is electric field times electric charge. So the larger the electric field that is applied, the bigger this current becomes. And then we move here. Okay.
Okay, and yes, okay. And the fact is that a certain moment of the electric field, you have a sort of a top of the resistance, and
yes.
With a bigger electric field, it go down.
Yeah, exactly. So yes, so there's a maximum because so when it goes up, we are in this regime. Okay, so the electrons scatter off the walls and the impurities, and so the resistance grows if the current grows. But then after this maximum, there's a crossover to this regime where the electrons kind of collectively move through the fluid as
the fact was discovered always already before. It's a classical effect, not a quantum effect.
Yeah, in some sense, it's a classical effect. But of course, quantum mechanics plays a role. I mean, this macroscopic realization is classical, but the quantum nature comes from the fact because this scattering length is determined by the coupling constant, and the coupling constant is of course quantum mechanics. Also, this relation here is calculated quantum mechanically.
So this effect is larger if the coupling constant is larger.
Yes.
So with the IDS CFT, when that is useful to calculate these cases in which the coupling constant is very high, it is possible to make the calculation.
Yes, exactly. That's the idea. Yes, exactly, okay. Precisely. Yes, thank you. Very good. Yes. This is exactly what I wanted to say. Thank you. Okay. Good. So I will come to ADS-CFT in a moment, but let me just explain a little more where people measure such effects. And so the prototypical material is graphene. Okay, so graphene is made out of carbon, but there's this beautiful hexagonal structure. So and this is a very pure structure with very little impurities. And so this is very suited for doing these hydrodynamics experiments. And also another word I have to introduce is this word Dirac material. Okay, so this is very important for applying ADS-CFT. So here we have the so-called Brimmer and Sohn, which you probably know. Okay, so this is in condensed matter people. Condensed matter physics people transform to Fourier to momentum space, and then there's this so-called band structure which gives you the dispersion relation of the electrons moving in this lattice. And so the interesting thing about this graphene is that there are some points where the two bands, I mean the valence and the conductance band, touch. Okay. And even more importantly is that here we have a region where there is a linear behavior. Okay, and if it's linear, it means that the energy is proportional to the momentum. And that's exactly what happens in relativistic physics, because in non-relativistic physics, the energy is proportional to the momentum squared. Okay, and then kind of artificially, effectively, these electrons look relativistic, although of course the Fermi velocity with which they move through the lattice is much smaller than the speed of light. Okay, so it's just an effective effect that you see in this medium. And since there's this linear behavior, if the electrons are in this region of the Bragg zone, they behave as relativistic particles. And that's of course very useful if you want to apply ADS-CFT, which relies on relativistic scenarios. Okay, there are some examples of ADS-CFT also for non-relativistic systems, but I mean, for better control, it's very good that we can use our relativistic approach. Okay. All right. So now here, I don't think I want to go through all the details, but I just want to say that people investigated the coupling strength for graphene quite a bit. And so they find it to be of order 1. So if the coupling is of order 1, we are just at the border of where strong coupling begins. Okay. So there are some arguments that in graphene, the electrons show this hydrodynamic behavior, but it's, we are just on the borderline of this effect. So it's not really 100% settled if what you see in graphene is really an effect of hydrodynamics or not. Okay. And so there were a lot of investigations of I'm just quoting some famous paper here, where people use kinetic theory. So this is the standard Boltzmann equation by which you determine how particles move semi-classically in some geometry, and they scatter off each other in the walls and so on. Okay, so in particular, people also considered eta over S in this perturbative approach and found it to behave with the temperature in such a way. Okay, so this is not so important for what follows. I just wanted to say this has also been investigated by very standard methods, but then it's more in the perturbative regime. So, but the important point is that here the coupling is of order 1, so we can see some effects of strong coupling kicking in, but it's still a bit borderline, and it would be nicer if this coupling is much larger than 1. Okay. Okay, I have some slides here about relativistic hydrodynamics, but probably I should skip this one now because I want to talk about where ADS-CFT comes into the game. Maybe we can come back to this at the end if you're interested. So the point is that we can use relativistic hydrodynamics, and since we have these long wavelength fluctuations, we can expand the fluctuations in derivatives of the thermodynamical quantities like the temperature, the energy density, the pressure, the velocity of the fluid. So U is this relativistic velocity of the fluid, P is the pressure, E is the energy density. And if we had an ideal fluid, then the energy momentum tensor would look like this. But now, since we have a fluid with friction, there are correction terms, and the correction terms will be organized in the number of derivatives appearing. So the first order correction has 1 derivative in every term. And this is exactly where this shear viscosity appears that I introduced yesterday. So yesterday I gave this very physical explanation what a shear viscosity is. But here you can see it appear in this more formal approach. Okay, so it's a first order friction coefficient in a derivative expansion of the energy momentum tensor. Okay, so for holographic hydrodynamics, I can just refer to what I was explaining yesterday when I explained, yesterday I already briefly explained how to calculate this famous result. And what is done is that we look at the propagation of a graviton, which is, so the graviton couples to this energy momentum tensor. And so from the propagation of the graviton in the dual gravity theory, that is governed to a particular action, the so-called Einstein-Hilbert action, which involves, so this is minus the determinant of the metric, the Ricci scalar, and the cosmological constant, which is negative in our case. And so again, it's very important to note these limits that I also discussed in quite some extent yesterday. So we have to send n to infinity. And this 't Hooft coupling here also has to be very large. And then in the strict limit where lambda also goes to infinity, ADS-CFT gives this result for eta over S. And so just to summarize what happens in this new paper that I'm about to explain. So in the new paper, we calculated the leading correction in the inverse 't Hooft coupling. So this is a result at infinite coupling, okay? So that's what I discussed yesterday. But of course, in real condensed matter physics, we never get infinite coupling. I mean, we get maybe some very big coupling, but not infinite one, okay? So then the question is, can we calculate corrections to this result in a kind of controlled way? And so what we did in this paper, which I'm about to explain, we calculated the corrections. So the corrections will be higher order in the curvature terms. So, you know, there's the Ricci scalar, but there's also the Ricci tensor and the Riemann curvature tensor. And so they can all contribute. And in higher orders, you have terms where there is the Riemann tensor squared, Riemann tensor to third power, fourth power, and so on. And these terms, they will give corrections to this leading result. And especially these couplings, because the couplings are in the regime where the coupling, these corrections are in the result where the these couplings are in the regime where the coupling, or the corrections are in the regime where the coupling is very small, is very large. And so the inverse will be very small. Okay, sorry, let me say this once again. So the corrections will be in the regime where the coupling is very large. So this means we have couplings in 1 over, corrections in 1 over the coupling, okay? So because corrections are always small, so in this case, the quantity that is small is 1 over the coupling, because the coupling itself is large. And in fact, as we showed, the corrections are in 1 over lambda to the 3/2. Okay, so there's a power of 3/2. Lambda is this 't Hooft coupling that is defined here. Okay, and actually the leading corrections to the known result will come from terms that are of 4th order in the curvature being added here to this action here. Okay, are there any questions about this? Okay, so we want to study corrections, and the corrections will be in 1 over lambda to the 3/2. And so they are corrections to the strong coupling result of ADS-CFT. And they will involve the 4th order of the curvature. Okay, so this is a quick summary of how the calculation works. And I explained this yesterday with my iPad, just to recapitulate very quickly. So this is exactly the same computation as we did for the quark-gluon plasma yesterday in this famous paper. The energy momentum tensor is dual to the graviton. So we have to use the so-called Kubo formula, which is related to the retarded Green's functions. And so we calculate the correlation function of this energy momentum tensor from propagation through the black hole space. And so, as I mentioned also briefly at the end last time, a finite temperature in ADS-CFT is introduced by putting a black hole into the anti-de Sitter space. And if you put a black hole in the anti-de Sitter space, then the Hawking temperature of this black hole naturally also gives you a finite temperature in the field theory at the boundary of the space. So the quantum field theory will be at finite temperature, and its gravity dual will be a black hole in anti-de Sitter space. Okay, and then you can calculate the entropy density, and the shear viscosity is obtained from this Kubo formula, and this leads to this famous result. Okay, so there's this brief remark about quantum critical systems, that the time scale then dominating the physics is this universal quantity h bar over k Boltzmann times the temperature. And so there might be some physical argument why you have h bar over k Boltzmann here. but the true non-trivial result of ADS-CFT is to get this factor of 1/4 pi here. And this, so far, it's very hard to get this by other methods. Okay, so that's just a brief summary of the computation I gave yesterday. So the statement is that we do exactly the same type of computation as for the quark-gluon plasma using the correspondence. So we calculate observables in the quantum field theory by using objects in the gravity theory. Okay. Okay, here there it's slightly more technical details about how to calculate these retarded Green's functions. So here, I mean, it's not just a correlation function, but in fact a retarded Green's function that enters the formula for the shear viscosity. And so the nice thing of having a black hole in anti-de Sitter space is that there's a very natural notion of causality.
May I ask?
Yeah, sure.
May I ask something? It is wonderful calculation. In the first lecture, you said that application of gauge gravity duality and theoretical relevance are not completely separated as many think.
Yeah.
And so I considering this general statement of you, I ask to you the fact that so beautiful calculation about the viscosity could be done with gravitational in a gravitational framework, according to you, means something from a physical point of view, either is only a calculation trick.
Okay, yeah, okay, that's, I mean, it's very hard to give a, you know, solid proven answer to this question. I mean, there's of course, you know, a little bit of wish and hope. I mean, because I mean, you know, okay, so there's obviously some features which make us believe that, you know, the fact, okay, so I guess the question is, why does ADS-CFT work so well for describing these strongly coupled systems? And does this tell us anything about quantum theories of gravity? And okay, of course, you know, since I work in this, I mean, I would say yes. I mean, here, this is, for instance, one particular example that we'll explain in a minute. So we have this very beautiful notion of causality happening automatically in this anti-de Sitter space, which we can then also use in the condensed matter physics. And then also now today in the second hour, I will talk a little bit about this quantum information relation to gravity. And so, you know, I would certainly say, you know, this teaches us about something about quantum gravity. And I think the notion where we can make this most precise is precisely in relation to the quantum nature of black holes. I mean, yesterday there were these beautiful lectures by Jonathan Bain on ER as EPR. I think this is a very beautiful example where ADS-CFT really fixes some properties of black holes. I mean, of course, these are black holes, the quantum properties of black holes. Of course, these are black holes in anti-de Sitter space, so they're not the black holes in the real world. But okay, as a first step, I think this is very promising. And so I think certainly it tells us, I mean, you know, something about the structure. I mean, I will come to this. So these correction terms, for instance, here, at least there's a consistency then of string theory models that is involved. Okay, so I will show you which corrections we can write down here. And given the ones that are relevant in this model, and there's also, it tells us something about the consistency of this string theory. I mean, of course, this comes as a limit of string theory here. And so, okay, to give a short and hopefully precise answer to your question. So I mean, there are some consistency arguments, given that these strongly coupled systems describe well things that happen in nature. And and these consistency arguments constrain quantum gravity theories to some extent. I mean, of course, not completely, but they give some insight into how these theories can look like. And that's one thing. And the example where this is working best at the moment is really for understanding the quantum nature of black holes. So that would be my answer for now. So the answer is there's clearly some hints that the consistency of these strongly coupled field theories requires a particular structure of the quantum gravity theories. But I mean, you know, we should be honest. I mean, this is very far from being completely understood. I mean, there are some hints, you know, how quantum gravity theories will look like, but and some constraints that fix the structure of the theory, but these constraints are not so strong that, you know, we immediately know what quantum gravity is going to be. I mean, I mean, there's still a long way to go. But I should definitely say that over the last 10 years, there was a tremendous amount of progress in understanding, for instance, the quantum nature of black holes at the theoretical level. And
so in a certain sense, you're saying that the fact that so beautiful calculation could be done is more important to understand better gravity than to understand better condensed matter.
No, this is okay.
Condensed matter that enlight gravity and not vice versa.
Well, okay. So maybe let me go on for a few slides. I mean, I think what the upshot of this paper really is that we can really calculate something for condensed matter, which nobody else can calculate with other methods. And it's also a very important result for condensed matter. Okay. So, okay, let me go on for a few, so because the next 3 or 4 slides, they will really be in the other direction. So where I want to use quantum gravity or ADS-CFT engaged gravity duality to learn something about condensed matter physics. And so this is a very beautiful example where we can say something about condensed matter physics that condensed matter physicists by their methods would never have found in this way, okay? And so I think what I claim is that there's this dual relation really that progress that helps us to better understand condensed matter physics, on the other hand, will also help us to better understand quantum gravity. So it's a both two-sided thing, and you cannot, I mean, you cannot say one is more important than the other. I mean, they go hand in hand, and when we make progress in one direction, we also make progress in the other. So that's what I would like to claim. So let me show this example. So to explain the logic of where I'm going. So the next slides, I really want to make use of ADS-CFT to learn something new about condensed matter physics, and we really find a very striking result, which is not possible to find by traditional condensed matter physics methods. Okay. Okay. So this slide was just to show, so this is the boundary of our anti-de Sitter space, and here we see so time goes in this direction, and this is the radial direction of anti-de Sitter. So the condensed matter system that would sit here on the boundary at this blue line, and then we have a past and a future horizon, and so there's particles, or the dual fluctuations come either from the past or they go to the future. And those from the past, they would give rise to the advanced Green's functions, and the one going to the future, they will correspond to the retarded Green's functions. So the black hole structure gives a very nice natural way of including causality into our condensed matter calculation. Okay, so now for applications in condensed matter physics. So this framework that I just presented, we applied to the so-called Kagome materials. So what is that? So Kagome is a Japanese basket weaving pattern, which leads to this hexagonal structure that you see here. And these materials, they really exist. Okay, so they have been synthesized in 2018. And okay, so here I just list some buzzwords that condensed matter physicists like to hear. So they have some very nice properties, and that's explained here. Okay, so now we look at this very particular cargo-me metal, which is the so-called Herbert Smithite, named after this American mineralogist called Herbert Smith. And so this is something that is really there. I mean, there's a picture in Wikipedia of this material, which you can see here. Yeah. Okay, so here you see the chemical composition of this material. So it has zinc, it has copper, oxygen, hydrogen, and chlorine. And precisely this material has this hexagonal structure, which you see here. And so if I'm not mistaken, so the green is the chlorine, the orange is this zinc, the blue is the copper, the red is the oxygen, and the white is the hydrogen. Okay, so, and it makes this hexagonal structure, beautiful hexagonal lattices. Okay, so this is something that is absolutely real. Okay. Now, the problem is that this absolutely real material doesn't quite exactly have the property that we want, because so these zinc, so note that there's zinc here, okay? And so this is a twice positive ion. And that implies that the so-called Fermi surface is below the Dirac point. So we have this band structure with this linear crossing, so where we have this quasi linear behavior, so this effective linear behavior here, so this effective relativistic behavior. But the problem is that the Fermi surface that tells us how much is the band filled by the electron, where the band is filled up to here. Okay, but to have this Dirac material, what we really would like is that the Fermi surface sits exactly at this point. Okay, so the electrons should be precisely here and then move in this dispersion in this band with this linear dispersion relation, because then they have this quasi-relativistic behavior. And now the ideas of the suggestion of our colleagues in condensed matter is to look at this, replace the zinc by scandium, which is 3 times positive. And that would have the effect to precisely lift the Fermi surface, so this blue rectangle, from being down here to being exactly at this point. Okay, so the idea is to propose a new material which has this interesting behavior, which is precisely what we want for ADS-CFT. Okay, and then of course, this is for chemists, this is a major thing to replace one atom everywhere in the material by another one. And so it's not quite clear if this can be done, but this is what we suggested in this paper. Okay, and then again, we get this very nice hexagonal structure. Now, so this is the same as before, but now instead of the zinc atoms that were there, we now have scandium sitting at these gray places, and everything else should remain the same. But okay, so that's the proposal, that it would be useful to try and synthesize this material. Okay, and now, so let me just flash, I don't want to go into any details here, but just to show that our colleagues from condensed matter physics, they did very prototypical calculations in condensed matter to characterize this proposed new material. So they calculate the band structure and they calculate the phonon dispersion. And so one important point here is that, so it's really a Dirac material, so the energy sits, the electron sits here. But the opening angle of this cone is bigger than in graphene. And because the Fermi velocity entered the denominator of the coupling, so it means that since now the opening angle is bigger, the Fermi velocity is smaller, but then the coupling is stronger. Okay, and so if we have the stronger coupling, then ADS-CFT can be applied better. And our colleagues also checked that there are not too many phonons around here until a reasonable temperature reachable in the lab, which would destroy all this beautiful structure that I was explaining. Okay, so, and then our colleagues in condensed matter, they calculated the Fermi velocity, the permeability, and the effective coupling constant. And the upshot is that in this putative new material called scandium Herbert Smithite, the coupling would be 2.9, roughly 3, say. And so in graphene, the coupling is 1. So if this material exists, the coupling constant would be 3 times bigger than in graphene, and then we would see more hydrodynamics. Okay, so that's the suggestion. Let's try to make this material, because then the coupling constant is 3 times smaller, and we are really a quite strong coupling where we can apply ADS-CFT well. Okay, so now what we did with this ADS-CFT computation, and so this is something which is really of interest to condensed matter physics, and and this is very hard to calculate with other methods, because if the coupling were really 3, then it means we can't do perturbation theory anymore, and then some other methods have to be used, and the methods we suggest here is ADS-CFT. And okay, so here again we see our nice result for eta over S that I explained before. But now we went away from this limit where the TÜV coupling is absolutely infinite, and we calculated the first correction now in terms of the coupling constant between the electrons. Okay, and so we find it to look like this. So on general terms, however, there is an issue now, because if we start looking at these corrections, okay, this is again a question to string theory and quantum gravity. We don't know what this coefficient is. Okay, so this is an undetermined, and we go outside this regime of universality. So not everything is fixed just by natural constants, but there are some terms which depend on the model. Okay, so we would have to fix a particular model, and then it's a bit hard to say which one. But so to quantify our ignorance, we varied this coefficient over 4 orders of magnitude. Okay, so this is a very big range. And we found that actually the size of the C doesn't make a very, very big difference. And that's very interesting. Okay, so here there's now this computation that we did on the gravity side. So to get these corrections to this eta over S, we have to study higher order curvature terms in the gravity computation. So instead of this Einstein-Hilbert that we looked at before, we look now at terms which are 2nd, 3rd, and 4th order in the curvature. And okay, so this is just an abbreviation. This could also be the Riemann tensor squared. So then there would be R mu nu sigma rho, R mu nu sigma rho, and so on. And now we can again use arguments from string theory. There's some topological argument, and also we can use some old results in string theory to show that the R cubed terms are absent. So there's string theory arguments why these 2 terms don't contribute. And the important term is actually the R to the 4th term. And that precisely gives us this dependence on alpha to the 3/2. Okay, but the price we pay is now that the correction is model dependent, although the 1st order term wasn't model dependent. And this model dependence is now parameterized by varying this coefficient C. Okay, so, and this is now the nice result where we combine the condensed matter and ADS-CFT. Okay, so here we have the effect of electron-electron coupling. Here we have eta over S, so our shear viscosity over entropy density in units of h bar over 4 pi k Boltzmann. And so in the infinite, so if the coupling were infinite, the result would be 1 over 4 pi. So in these units, it's just 1. So this would correspond to this red dashed line here. Okay. And so now, if we go to infinite coupling, the holographic result would be just 1 over 4 pi. But now we calculated this correction. And so the correction goes like alpha to the minus 3/2, so it goes like this. But now there's this uncertainty from this model-dependent coefficient, but it turns out that if we vary this coefficient for 4 orders of magnitude, it just sweeps out this gray band here. So the results will all be in this gray band. So, and we see there's a very little effect of this. So if we change this coefficient by 4 orders of magnitude, here it just changes by a factor of 2, say. Okay, so that's reassuring. And so graphene, which is now used for hydrodynamic behavior, sits here. And this new material that we suggest together with the condensed matter physicists is at much larger coupling. And then we see in this regime, this would already be much smaller, so much closer to this asymptotic holographic value. And so that provides extra motivation for actually obtaining this material in the lab, because then it would be very useful for this hydrodynamic behavior and for testing predictions of ADS-CFT. Okay. And now, so the upshot at the end is that if we reach this point with this new material, then we would also have some very nice new behavior, because we can actually estimate that that's a regime where turbulence is possible. Okay, so then if it's possible to make this material, then there would be a turbulent behavior of this electron flow. It wouldn't just be a laminar flow, but something with very nonlinear behavior, and which cannot happen in graphene, but it could potentially happen in this new material. So that would be very interesting. Okay, so now to come back to the question that Professor Fano asked. So this is really now, I mean, the motivation for this calculation is really to use ADS-CFT to learn something about condensed matter physics. And so we managed to calculate something that wasn't possible to calculate with any other methods in the strong coupling regime. And so this is a result which is really of great interest to condensed matter physicists also. Okay, but then once we finish this calculation, we can say, okay, it's great that it works so well. Now, can we also learn something about quantum gravity from this? And well, okay, so we can just make a very modest statement, which is that the consistency required to get this result here puts some rather weak constraints on the quantum gravity theories that we need to look at. But okay, it's certainly, I mean, there's some information on what I mean. So this is a kind of effective theory that comes from string theory in some limit, and certainly the result puts some consistency conditions on these type of actions as well. So you know, there's certainly also some information going the other way, but clearly here the motivation was to make a prediction for a material in condensed matter physics that's not possible to obtain in any other way. Now, if we want to learn more about quantum gravity, I think it will be useful to look at these quantum information aspects, and that's what I'm going to talk about in the last period. So I think now it's good to stop here with the condensed matter and just ask if there are further questions.
Maybe can I just ask you something about that factor of C?
Yes.
C. So, I mean, you said that you can interpret it in terms of this R4 term, and I was interested in two things, like what is the physical interpretation in the gravity theory of this R4 term, and also if there are any proposals regarding the microscopic interpretation of this term, which, if I understand correctly, should in some sense be interpreted in string theory, right?
Yes, exactly. Yes. Okay, so yeah, so let me just say that alpha is the effective electron-electron coupling, so it's related to the lambda. So so the TUF coupling lambda is actually alpha times n. Okay, but the dependence on n we kind of included now in this coefficient, in this unknown coefficient, because of course condensed matter systems are not large n. Okay, this is another example where we exploit this universal nature, but you know, have to make some statements about this factor of n. So in this case, the factor of n is absorbed in this unknown coefficient. Okay, so alpha is the electron-electron effective interaction. G squared was called beforehand. Okay, so so then yeah, if you have a consistent theory of string theory, this should fix this coefficient C. Which we relate us to these. So here we argue that gamma 2 and gamma 3 actually vanish, but we have, I mean, this gamma 4 can have different values depending on which string theory model you're looking at. But then similarly to yesterday, when I described models for QCD, I mean, we couldn't just use the original ADS-CFT correspondence. So we had to break the symmetries, we had to add more degrees of freedom and so on. And certainly the same would happen here. We have to break the symmetries and add more degrees of freedom and so on. And then it becomes very hard to make any statements about what this gamma should be. Okay. However, okay, now we could be very bold. So if it's actually possible to make this material, yeah, so, okay, I should emphasize again, this material doesn't exist yet. We just suggested to make it, okay. And should this exist and show that, you know, we are actually, well, so we predict the result for eta over S should be somewhere in this band. And if this number were actually known, I mean, that would certainly then say, okay, this particular condensed matter model is fixed by a particular value of this gamma, yeah, and that would then correspond to a particular string theory model if you want. Okay, I mean, I'm sure this wouldn't tell you, I mean, we have to be careful again because all these actions are in anti-de Sitter space. I mean, it's not string theory describing the real world, it's still string theory in this kind of artificial mathematical construction, but certainly, I mean, that would tell us that this particular condensed matter model leads to a particular coefficient here in the string theory action. But okay, I don't think that would really tell us anything about string theory as a theory of quantum gravity in the real world. I mean, it would just put some additional information on this particular case where we look at string theory in anti-de Sitter space. Did that answer your question?
I think Pedro has a question.
Yeah.
Yeah, it's basically a follow-up on, because I had basically the same concerns as Professor Vano, and so perhaps after your second part of the thing that I'm a bit concerned is, I mean, the consistency, because unless I missed the example yesterday about quark-gluon plasma, in that example, there is no use of a black hole in ADS, is there?
No, yes, of course there is.
So there is also
yeah,
a
there
black
is, because sorry, for the quark-gluon plasma, we need the finite temperature. So the quark plasma is at finite temperature, but also it essentially enters this calculation in presence of the black hole. Yeah.
So the bottom line is that the results that basically you are using with the aid of gauge gravity duality, I mean, they all seem to imply a black hole in ADS, right?
No, okay, no, that's not quite true. I mean, in the example for the
that's basically my kind of worry, because if in some examples there is no black hole, so yeah, I may be wrong in which particular example you do use and you do not use a black hole. But the point is that
go ahead.
The point is that there must be some sort of consistency in basically, it's not only that basically get the results right in basically in condensed matter or nuclear physics, but also that the ADS side of the duality is kind of consistent, because it seems a bit puzzled to me. I mean, that basically you do involve a black hole in ADS for some particular system in condensed matter or nuclear physics, and then in other examples which perhaps are not that far in terms of basically the energies involved, because they are all low energy. Of course, they are different physical subsystems, but in some other examples, you do not basically involve a black hole in order to yield the predicted result. So it's
okay,
kind of...
let me answer the question. Okay, let me just say, yesterday I had one example without temperature. So this was the example of the mesons. Okay, so that was calculated at 0 temperature. So there was no black hole in that case. And the other examples I had, like the shear viscosity and today's example, they were involving a black hole, so they were at finite temperature. Okay, I really don't see this issue at all. Sorry, because I mean, I will explain this a little bit now, actually. So
Yeah, no, perhaps.
putting a black hole into the ADS space just means that in a very natural way, we include a finite temperature in the field theory. But of course, also in the real world, I mean, you know, there are some examples where temperature doesn't matter. I mean, if you do QCD for the LHC collider, nobody worries about whether there's a, I mean, everything is done at 0 temperature, okay? So I use a model where there's 0 temperature, but then there's other models where the temperature is very important, like condensed matter physics or nuclear physics. And then I look at a model where there's a black hole. I mean, what is the problem? I just choose a model appropriate to the situation I'm looking at.
Yeah, no, my concern is that it seemed awkward to resort to a black holes just in order to mimic a finite temperature system.
No, okay, but this is supernatural. Okay, then let me show my next slides, because I was exactly going to talk about this. Okay, but unfortunately, okay, maybe I have to resort to drawing some pictures again. Okay, let me just first take my slides. Okay, let me share as first here. Okay, can you see the slides? Okay, maybe let me not, it always takes a while, because I also want to write something in iPad in a second. Okay, so now the last part is called relating the quantum structure of black holes to quantum information. Okay, and okay, so black holes. So there has been recent progress in the real world because they were directly observed from looking at gravitational waves. So the fact that there's these gravitational waves emitted from black hole mergers really means that there's black holes in the universe. And so this is a major development in astronomy, which is pretty recent, okay? And but that's of course classical physics, but so black holes really exist, okay? So, but then the question is, what exactly happens inside a black hole? And after Hawking, we know that they have important quantum aspects. And now, due to the Wittgenstein-Hawking formula, so they also have important quantum properties, and that these are related to the entropy and so to information. Okay, and so this is a big topic now in theoretical physics. Okay, on the other hand, we have quantum information, which is about processing qubits and entangled states. And so now actually recently via ADS-CFT, there's quite a lot of new relations between the quantum aspects of black holes and the processing of qubits. Sorry. Okay, so gauge gravity duality provides new unexpected links between both of these areas. Okay, so this is this picture from the Event Horizon Telescope. And so a black hole is a gravity object with remarkable quantum properties. It's very massive. And because it's so massive, there's a strong curvature of the space. And then importantly, black holes, they have the Schwarzschild radius. So once matter or light passes the Schwarzschild radius, it's trapped inside the black hole and cannot escape anymore. So this is our space-time, and then here we have a space-time singularity, which is a black hole, and then here's the Schwarzschild horizon, and so if particles fall into the black hole, then they have disappeared if you look from the outside. Okay, so there's this new direct observation from gravitational waves of black holes in the universe, so in flat space or de Sitter space. And okay, so here, okay, let's look at the metric, and maybe this answers a few of your questions that you had. Okay, so this is a metric for a black hole in flat space. And then you see there's one function here and the inverse of this function here, which depends on the radial coordinate. So this Z coordinate would be this coordinate here going in the radial direction here. And so if we are in 3+1 dimensions like our real world, then this function looks like this 1 minus Z over ZH. So ZH is the radial value at the Schwarzschild horizon, which in this picture is just a circle here. Okay, and now you see something terrible happening when this coordinate Z reaches the horizon, okay? because then this factor is 1. Then you have 1 minus 1, and 1 minus 1 is 0. Okay, but if this function is 0, then somehow the space becomes very degenerate here. Okay. This means when up the Schwarzschild horizon, the space-time, at least in these coordinates, something strange happens in the space-time. But so the question, what happens actually at this place, is very much related to which coordinates you choose, and a better coordinate system to choose is to use the so-called Kruskal coordinates. And then we can determine the causal structure of the space-time when there's a black hole. Okay, so a light ray travels along, so if we just look at 2 dimensions, okay, such that I can draw nicely here on my transparency, then a light ray travels along x is equal to t. Oh, 1 second. Erdmenge. Ja. Oh, perfekt. Dann komme ich heute Nachmittag. Ist gerade angekommen. Dann komme ich heute Nachmittag vorbei. Herzlichen Dank. Bis dann. Auf Wiederhören. Tschüss. Okay, sorry about this. Okay, so then I can look at a light ray traveling in this diagram where here there's space and time, and if I set c equal to the speed of light equal to 1, then my light travels along this direction here. And this defines the so-called light cone. So if I'm sitting here, then my future is inside this blue area in the future, and my past was influenced here below by this region here. And this is the causal structure of flat space-time, because if I'm sitting here, I cannot influence any physics that's there, because that's too, I would have to travel faster than the speed of light. So I can influence anything that is in this region here, and I'm influenced by anything that's in the past. And also in the future, I can only travel in this direction. Okay, so now what happens for a black hole? Well, if I'm very far away from the black hole, so essentially, oops, sorry, that was the wrong. If I'm very far away from the black hole, so if I'm here, okay, then I'm again in flat space. And so my light cone, my causal space-time looks exactly the same as in a flat space, okay? But then when I approach the black hole, so this is the radius of the black hole, so the Schwarzschild radius, then due to the curvature of space, my my light cone starts to deform, and especially this one side of the light cone starts to move up like this, okay? And once I reach the Schwarzschild horizon, my future is entirely inside the black hole, and I cannot escape anymore, okay? So I can only go to this region. This means I cannot go to regions outside the black hole anymore. Okay, so this is the causal structure of the black hole that's super important for understanding their physics. And so once I'm here, I don't really notice anything special, except that, so falling through this black hole horizon, I don't notice anything except that I'm trapped and I cannot leave this anymore in the future. Okay, so that's the causal structure. And so in fact, when you do some calculation, which I should have shown to you since you're asking, but I now haven't done it, unfortunately, but let me just quickly try to explain. So to have a meaningful, okay, maybe I should take a piece of paper. Okay, so this is just a piece of, can you see me taking this piece of paper? Okay. So something, so you see that the space-time coordinate becomes slightly degenerate when z is equal to zh. And so what we have to do, we can still ensure a regular spacetime. So the spacetime here is still regular. Okay, so here I have chosen a different coordinate system. This is in the so-called Eddington-Finkelstein coordinates, whereas this is in the Schwarzschild coordinates. So the Schwarzschild coordinates are not very useful once you go past the horizon, because there's this singularity happening here. But so for what happens from the physics is that you need to compactify this coordinate on a circle. And so what you want to avoid when you sit here is that you want to avoid a conical singularity. Okay, so you want this, so this space, I hope you can see what I'm doing. Okay, so this space-time has a singularity here. And that's something you don't want. Okay, so when we fall into the black hole, nothing really terrible happens. So which means the space-time locally must be regular. So it must be flat. And this means that this time component here, in some suitable units where you divide by the radius, must be an angle of 2 pi. So okay, if my space is like this, if I'm around my hole, okay, there's an angle of 2 pi. But if I do this, the angle is smaller than 2 pi, and then I get a singularity. So I have to ensure that in this time direction, I have a circle with a particular radius given by the geometry, but then I have to go around the full 2 pi angle. Okay. And so this means I have to compactify this time direction on a circle. And compactifying a time direction on a circle is precisely giving you a finite temperature. So people working in quantum field theory, when they want to impose a finite temperature, they do precisely the same. They compactify the time on a circle of radius with an angle 2 pi going all the way around 2 pi. And that leads to finite temperature field theory. There's the Matsubara frequencies and things like this. Okay, so we have to make sure that we have this regular behavior, and this regular behavior. So the regular behavior that we have to impose for the black hole corresponds precisely, formally, mathematically, to having a finite temperature in the field theory. And so this, or put differently, the same way in which I ensure a regular space for the black hole, a regular metric for the black hole, is the same procedure as introducing a finite temperature in the dual field theory. Okay, so okay, so let me jump this because this I think I explained already. So here, this is what I wanted to say. Black holes in hyperbolic spacetimes are marked to strongly coupled quantum field theories at finite temperature. So that's applying gauge gravity duality to finite temperature. Okay, so putting a black hole in an anti-de Sitter space, I have to ensure some particular regularity condition, and this regularity condition implies that my field theory is at finite temperature. So this is a well-defined mathematical procedure. Okay, so now coming to your question. So I can consider ADS-CFT in the way I did at the beginning at 0 temperature, which just means I don't have any black hole. Now, then I can say, okay, let's look at different, slightly more complicated geometry in the same way as this metric I just showed with this compactified circle. And then I have a gravity theory at finite temperature, or I have a gravity theory with a black hole that automatically, by the argument I have just given, corresponds to the field theory at finite temperature. Okay, but this is just a mathematical construction because my black hole is in an anti-de Sitter space. I mean, it's not a real black hole. I just have a gravity theory in which black holes in anti-de Sitter space are solutions to the equations of motion. And now, if I wanted to use ADS-CFT to model something at finite temperature, then I will put this black hole in some other case where I'm not interested in the temperature, I just consider a space without a black hole, and it's also consistent. Okay, so
Yeah, okay. So yeah, I see your points. So then my worry stands, because it seems that just this black hole is a device, in the sense, as you just yourself said. I mean, this is a black hole in ADS, so it's not we cannot infer basically from basically the results in the gravity, in the gauge theory, in say quark-gluon plasma, or this ratio that you've been shown, that basically anything about at least it's hard to basically say that what geometry of the dual ADS theory looks like, because you are saying that, well, it's just a matter of whether I'm interested in basically zero finite temperature. So
yeah, exactly. But that's I said all the way along.
yeah, no, I know.
I never claimed I would, I mean, before to answer Professor Fano's question, I said, okay, the fact
Yeah,
that
sorry, no, you don't have to go again, because I don't want to basically disrupt the flow of the, because I just wanted to press on this thing that, okay.
Yeah, but I want to answer your question. Okay, let me say this. So okay, I'm at the moment I'm making models using dual gravity theories. Okay, but nevertheless, okay, I think my answer to Professor Sano's question was much more subtle. Okay, so nevertheless, I would still claim that the fact that it matches well to some theory in condensed matter physics, quark-gluon plasma, gives some consistency condition at an abstract level how these string theories should look like, but not at this very prominent basic level of whether I have a black hole or not. I mean, but also in our universe, there's regions where there's no black holes, and other regions there are black holes, and okay, fine. But okay, there's still, I would claim that, this fact that these theories describe condensed matter well, still give a consistency at an abstract mathematical level to these quantum theories of gravities, but it's maybe now a bit too complicated exactly at what level. Okay, but the level is more sophisticated than just having a black hole or not. Okay, so good. Okay, so in the last part now, let me go to this quantum information. Okay, so another important feature of black holes is this Bekenstein-Hawkins formula, okay, which I showed on the previous slide. Okay, so the information content of a black hole is encoded in their horizon area. Now we can combine these two things together. Okay, so we know black holes in hyperbolic spacetimes are mapped to strongly coupled quantum field theories at finite temperature. And information stored in the black hole is mapped to information stored in the quantum field theory. So now this suggests to use quantum concepts from quantum information to learn more about these black holes in anti-de Sitter space. Okay, but there's a technical issue there, which is actually quite a significant technical issue, that normally quantum information is done for a small amount of degrees of freedom. Okay, so for instance, say you have a system with several entangled spins, let's say a number 10 or so. Okay, so 10 entangled spins, they have a particular finite amount of degree of freedom. But the problem here is we want to have these quantum information concepts in a quantum field theory, and quantum field theory by definition always has an infinite amount of degrees of freedom. So if we want to use quantum information to learn something about the quantum nature of black holes, we have to extend these quantum information concepts to infinite dimensional Hilbert spaces. And that's not always very easy to do. Okay, so that's actually quite involved. But many new things were learned by doing this in the last couple of years in theoretical physics. And let me just show some examples. Okay, the starting point of any analysis of quantum information in gauge gravity duality is this Ryo-Takayanagi formula for the entanglement entropy. So I don't know, should I explain this again, or should I move to another example right away? I mean, I should explain, should I go I mean, you know, I don't know, was this covered already before the lecture? No, or?
I think it has already come out in the lecture, so if you want to discuss maybe different example, I think it's fine. Otherwise, we will find through here again about the dynamic problem. Not,
Okay, good. Let me very quickly go through it anyway. So the starting point of looking at quantum information concepts in gauge gravity duality is to look at the holographic realization of entanglement entropy, which was proposed first in this paper. So, and the proposal made here, which, okay, of course, again, because ADS-CFT is a conjecture, is also a conjecture, is that the leading term in the entanglement entropy is given by, in the dual theory, by an area of minimal surface in the holographic dimension. So this means if I have a region A and B, and they are separated by this circle, then the entanglement entropy between these two regions is given by the area of this surface here. That's the proposal. And there's some very good reasons why this proposal should hold. And although it's a conjecture, there are some very good reasons that explain why this works. Okay. So of course, a key feature of quantum information is to use entangled states rather than just product states. And these are described by density matrices that you see here. So then there's the so-called von Neumann entropy, which is the standard Boltzmann entropy applied to this density matrix. Now you can check that this is maximized when rho is diagonal with equal entries. So then there's very little information, and it vanishes for pure states when actually this is just a projection operator and rho squared is equal to rho. Okay, now consider a product Hilbert space of this type. And then we can define a reduced density matrix rho A by tracing over those degrees of freedom that an Hilbert space B. And then the entanglement entropy is just defined via this reduced density matrix. And there's already an analogy to the black hole information, because by this tracing, we lose some information. Okay, so somehow the entanglement entropy measures the lost information hidden in this area B. Okay, so here's again the formula for this Ryo-Takayanagi proposal. And so actually it satisfies many conditions that you would impose to make a meaningful entanglement entropy, and they're satisfied. Okay, and then actually a very good reason why this conjecture is true is that it really works well in at least in a simple example of a conformal field theory in 1+1 dimensions, studied by these famous authors, Cardi and Calabrese. So they calculated this in this quantum field theory, and they found a particular result. So C is the central charge of this conformal field theory, L is the length of the entangling region, and lambda is a cutoff. And precisely this equation is reproduced by this minimal area, which in this low dimensions just amounts to a geodesic, the length of a geodesic. In this very low dimensions, you just have to calculate the length of a geodesic instead of a higher dimensional area. And actually, the quantum field theory cutoff is replaced by a boundary cutoff. And according to the rules of ADS-CFT, the central charge is related to the ADS ratios and the three-dimensional Newton constant. And putting everything together, then the Ryo-Takayanagi result exactly coincides with this field theory result, which I think is a very remarkable result. Again, we can do the same calculation at finite temperature by putting a black hole into our antidissonant space. And then you have a temperature dependence that is given by this equation here. Okay. So it's really remarkable, again, very remarkable that you have these two very different calculations. So a complicated Rivlin trick calculation in conformal field theory and the length of this geodesic, and they really both give the same result, which is this one. Okay, so that was my lightning review of the entanglement entropy. And so now I would like to discuss for you another example, which is the so-called complexity. So so entanglement entropy was the first observable that people used to use quantum information concepts in gauge-Rabi duality, but another one is this complexity. So also called quantum computational complexity. Now let me explain what this is. Yeah. So again, this is a concept from quantum information theory in the real world. So this means it was first found for systems with a finite dimensional Hilbert space, and so exactly here the problem is again to translate this to an infinite dimensional Hilbert space. Okay, so in the case of quantum information theory, where we talk about finite dimensional Hilbert spaces, let's look at the definition of this complexity. So the idea is to consider a set of predefined unitary transformation in a Hilbert space. Okay, so imagine you want to build a quantum computer and you have a very, very simple and small quantum computer, which is made out of 10 spins. Okay, you have 10 spins and they can either point up or down. Okay, so this is your quantum computer. Then in your lab, maybe you have some device that you want to do some computations, then you obviously have to change these spins. And imagine you have some device that flips a certain amount of these spins. So these predefined unitary transformations could, for instance, be flip the first and the 7th spin, or flip the 2nd, the 8th, and the 9th spin, or something like this. And so then the question is, how many of these operations do I need to apply to reach any given state from a reference state? So say you start with some state, this is your reference state in your Hilbert space, and then you ask how many of these predefined unitary transformations do I have to apply to reach any other given state in the Hilbert space. Okay, so this is really, if you want to do some computation in quantum information theory, you start with some configuration of spins, and then you apply a given number of these unitary transformation, and then you get another configuration of your spins. Okay, and then the number of these is called the complexity. So because obviously if you have to apply many of these, then it's more complex than if you just have to do this once. Okay, so this is an observable that is used in quantum information to explain how complicated a particular calculation is. And so now I can also write this in a formula. So then our reference state would be some state in a Hilbert space, and then we have a set of unitary operators which lead to these transformations. So they are called gates. So, and now I have a mathematical definition of what I just said before. So the complexity of the state, the complexity C of psi of a state psi, is given by the minimal number of gates required to map the reference state to this final state up to a given tolerance. Okay, so the complexity is the minimal number of these U's that I need to apply to my R to get some other state. So, and for a complicated complex calculation, of course, the complexity is bigger than for a small number. And also the complexity is called, so the complexity is linear in time, because if each operation takes the same amount of time, then if you do more steps, then it will grow linearly in time. Okay, so this is very important to compare to black holes. Okay, so now the issue is that this quantity is well defined for pure states in a finite dimensional Hilbert space, but if we want to make any relation to black holes, we need a definition for quantum field theories. And okay, this is a huge area of research. I mean, there are many people working on this, including myself. How can we define this quantum complexity for a quantum field theory where we have an infinite amount of degrees of freedom and we also have an infinite amount of gates? Okay. Of course, if you have an infinite amount of gates, this concept becomes a little trivial, because then you just apply one and you get your result. Okay, so and then you have to define a subset which is valid also. So it's not so straightforward to do. So there's a lot of work on implementing this. Okay, so why is this interesting? Because Leonard Susskind, very famous theoretical physicist, proposed a holographic dual of this complexity for black holes. Okay, and so this I would like to show here, and it's also nice because there's some connection to the lecture by Jonathan Bain of yesterday. Okay, so again, let's go to this picture which I showed before. So where this is, we have now 2 copies of the boundary. So there's one boundary with a CFT here and another copy of this theory with on this boundary on the other side. This is our black hole, the past singularity, the future singularity, just as I showed you in the preceding hour. And then we can look at geodesics that go through this black hole configurations, and they really look like wormholes. Okay, you go inside the black hole and come out again if you want. But okay, these wormholes are non-traversable. You can start on either side and just go inside, but of course you cannot come back from the black hole, and this is not possible. Okay, so and then as Jonathan Bain explained yesterday, there's this EPR proposal that you actually, if these 2 theories are entangled in the so-called thermophile double state, then you consider the entangled states of these theories, and so you have 2 copies of the same theory, and the states are entangled in this thermophile double. Okay, so that was defined yesterday in Jonathan Bain's lecture. And so now the idea of Susskind is that the length of this bridge, which is, because it's here and it's just drawn in this small dimension, so the volume is just the length of the curve. Okay. So the length of the curve is the volume, and so this volume should be a measure for this complexity. So the idea is that the gravity dual of the complexity will be the volume of this bridge. Okay, that's a very wild suggestion, okay? But there's some reason why this should be the case. And one reason is that this also grows linearly with time. If you calculate this volume as using the equations of motion for the gravity theory here, you find that it grows linearly in time. So for that reason, there's some feature which is similar to this complexity. Okay, now there's another proposal. So this is the complexity is equal to volume proposal, but then there's also a complexity is equal to action proposal. And there, rather than just using the volume, which is something kind of kinematical, not a dynamical, then we calculate the action on this causal patch here, which is the so-called Wheeler-DeWitt patch. And so we calculate the gravity action on this patch, and this has the same property of growing linearly with time. And so the question is, I mean, which of these is now actually realized in this duality? So this is an unanswered question, but this has really triggered a lot of significant research in the last couple of years. Okay. Okay, and okay, so maybe before I move on, are there any questions about this? Okay, I mean, this is really a conjecture, which is even more a conjecture than the ADS-CFT correspondence itself, okay? So, but it really triggered a lot of research because people tried to make sense of this, okay? So I should also say it satisfies a particular bound related, so, there's the so-called Lloyd bound, which is the bound from quantum information theory, which tells you that the complexity, the growth or the velocity with which the complexity grows has to be bounded by the energy of the system. And here the energy of the system is the black hole. And you can actually show that this relation is also satisfied by this proposal. Okay, so, but I was also involved in some work trying to make sense of this proposal and put more content or more evidence that this is actually true. And so let me just very briefly at the end flash some work that we did. So we looked at the so-called subregion complexity, which is a combination of the entanglement entropy and this complexity. And instead of looking at some very general volume as given here, we looked at the volume underneath a particular Ryotaka-Yanagi surface. And okay, I don't think I will have time to explain all the details, but I want to end the lectures with something nice. And the nice is the following. Okay, so there's some gravity calculations. Again, you can put a black hole, and there's some topological arguments about this complexity and so on. But also there's a relation to the so-called tensor networks. Okay. And so this is another concept in quantum information theory that now enter the game in the context of gauge gravity duality. And so these tensor networks, okay, I don't think I have really time to explain, but so this is a device from numerical quantum many-body physics where people organize Hilbert spaces in particular structures, and that leads to particular tensors that give you, you know, a direct product of states in a very complicated, very big Hilbert space. And then they end up with these kind of pictorial networks. Okay, so these are tensors that, you know, manipulate the states in this very big Hilbert space. But there's actually some of them, depending on the operations that are allowed, which actually have this structure very, very similar to a holographic space. Okay, so this tensor networks automatically lead to a geometry which looks very similar to this hyperboloid that we were discussing in these lectures here. And so yesterday I explained that in ADS-CFT, the extra dimension corresponds to the RG scale. And so precisely this appears also in these discrete tensor network constructions of space. And so that's also a very interesting relation between some quantum information concepts on one hand side and ADS-CFT on the other. Okay, the difference, of course, being that this is a discrete space, and in ADS-CFT we normally have continuous spaces. But okay, nevertheless, we see that we lose degrees of freedom as we go to the interior, which is precisely this RG concept. And also the metric of ADS, precisely, you know, due to this warp factor. You know, there were all these angels and devils very close at the boundary, but they are very sparse in the interior. So that's also something that you see here. Okay, I should probably stay here and stop here with the explicit examples, and let me just make some remarks, and then I'd be happy to take some more questions. So what I just wanted to flash very briefly here at the end, that so there's quite a lot of ongoing research now to use these concepts from quantum information theory to understand the properties of black holes in the dual ADS geometry, especially their quantum properties. And so the best understood example is this entanglement entropy. But there are also others. I mean, there's, for instance, this ER-EPR proposal is very important, and it also enters this quantum complexity proposal that I very briefly mentioned at the end. And so the idea is to use this approach from quantum information to learn something about the quantum structure of black holes. And there's been quite a lot of progress recently. I mean, we really know a little more about the quantum structure of black holes, their late time behavior than we did a few years ago. And yeah, so I think this is another nice example where we can use information in more quantum field theory related areas via the duality to learn more about the quantum nature of black holes. And so that brings me back to my general statement that I wanted, you know, to say that, you know, of course, I explained quite some detail why so far there is no proof of the ADS-CFT correspondence. And so I said that when I said no proof, I had my idea in mind is to prove the ADS-CFT correspondence using string theory and moraines and so on. But now maybe ADS-CFT or gauge gravity duality is a concept much more widely valid than string theory. And then maybe we have some other way of proving it, maybe using these quantum information concepts. However, of course, if we just start constructing these networks and so on, everything is much less constrained than in string theory. And so there are many choices, and it's a bit hard to say what to do. And we certainly have to do a lot more research to make a very concrete statement here. But certainly there's many interesting things to do, and it's a very lively area of research, and there's many things to be done, and I am very grateful for your attention, and I hope you had some fun also with my lectures. Thanks a lot, and I hope there's some more questions.
So yeah, I wanted to ask you something. I don't know if is there anyone. Something very quick on the complexity action proposal.
Yeah.
Which properties of the space-time do you fix by fixing the action the way of the width patch? So like what can you learn about this? What's going on in the space-time? Because for example, with the entanglement entropy of Takayanagi, you can in the end compute, for example, the entropy of the black hole and things like that. So is there any result along those lines maybe?
Yeah, okay. So yeah, I mean, the idea would be the same, that the proposal, I mean, if the proposal really works as it is suggested, I should say this proposal is much more speculative than the entanglement entropy, because for the entanglement entropy, there are actually calculations which you can do and you can compare and you get the same. For this complexity action or complexity volume, the proposal, I mean, if everything works to plan, then just if you compute this action or this volume, it should tell you about the complexity of the dual quantum field theory. The problem now being that we don't quite know what the complexity of a quantum field theory is. Okay, so for the complexity of for the entanglement entropy, it's very well defined what the entanglement entropy is, at least for a 1+1 dimensional CFT. But before we here in this context, we are one step further back. I mean, before we actually can make use of this proposal, we first have to define complexity for a quantum field theory, and that's not so easy because it's a concept from quantum information in finite Hilbert spaces, but now we have to define it for an infinite dimensional Hilbert space. And there's been many proposals what this could be, but it's not settled yet. And so for that reason, we are at one kind of lower step than the entanglement entropy proposal. But okay, so the idea would be that if we can somehow define the complexity of a operation in quantum field theory, like applying some unitary transformations, this should tell us something about the late time evolution of this quantum black hole. And so related idea which has been successfully addressed is the so-called Page curve. Okay, so I mean, this is something maybe I recommend to look up what the Page curve, PAGE curve is. So this describes the late time evolution of a black hole. So that first the entropy increases and then it decreases again. And this can be very nicely interpreted by a dual in the field theory. So, and with the complexity, we hope to reach a similar goal, but it's ongoing research, and the difficulty is to find a notion of complexity for infinite dimensional Hilbert spaces and for quantum field theories.
Right, thanks. So I think that is a question.
I would like to thank Johanna for her wonderful 4 lectures, for being so oriented to philosophical problems in her presentation. And I would like to say something about my question 1 hour ago. We have not a clear definition what is understanding, what is comprehension. Yeah. But it is clear that physics is not only prediction, but also understanding of the reality. Probably understanding is something connected to the simplicity of our equation, something connected with the possibility to have a good representation in state space, good analogical, good analogical shape, geometrical shape, and so on. There is many factors that make something comprehensible for us, for humans. But it is important because we push science not only for predicting, but also for understanding. Understanding is an important part of our life. In my opinion, the most important in a certain sense. And so when I asked at the beginning about the relation between condensed matter physics and the gravity, and I thought I understand very well that through RDS CFT duality you can make good calculation concerning condensed matter, as the one that you presented about the viscosity of glue and plasma. But my question is not only about calculation. It's clear that when we can calculate in a certain sense, at least partly we can also understand. But understanding something more. So my question is, when we make this kind of application of gravity, coming back to your statement that in a certain sense there is a strong connection between application and theoretical value of the SCFT duality. My question is the fact that the S duality can help us to make this calculation in condensed matters, help us to comprehend better condensed matter, either gravity, quantum gravity, or both, and in which sense? This is my question. I attempt to formulate it again the same question.
Yeah, okay. So, right, okay. Let me say, okay, so again, I think both of them are on a kind of equal footing, but I have to admit, I mean, you know, there's still a lot of research to be done before we really reach a level of comprehension, as you mentioned. I think that, you know, there are some beautiful examples. I mean, for instance, I mean, the shear viscosity example, and also this, I think the entanglement entropy example, especially in this 1+1 dimensional case. I think there we have a lot of understanding, because we can do, I mean, we do two calculations in two completely different scenarios, and the calculations look very different. And they're long and involved and complicated, but in the end of the day, we get exactly the same result. And this is super surprising, and this just is super fundamental, okay? So there, I would say there are these individual, nice, beautiful, super convincing examples, of which I've given a few in the lectures. And in those cases, we know quite well what is going on. And it would be nice to find more examples and eventually have a full comprehension of why these things are so closely related and so on. But I mean, it's not easy. And the reason why these beautiful examples where we understand a lot work well is just because of this universality. If, you know, the one problem is really the strong coupling that is in these models. I mean, the problem is if there's strong coupling, it's very, very hard to actually say what's going on, because in physics, normally we always make approximation where we say, okay, if there's an interaction first, this particle interacts with that particle and this with the, but if we only can treat the entire, I mean, physics is about making approximations. And if we have to describe everything at once and there's no way of approximating, then it becomes extremely hard to say anything about these systems. And those examples where things work so beautifully is where there's universality, which means the physics doesn't depend crucially on which degrees of freedom we have. And then it becomes more simple, and we know what we are doing, and we get these very, very beautiful examples. And so one problem of understanding in general, okay, beyond, say, the entanglement entropy, the shear viscosity, where it works so beautiful, is that then we would need to understand the dynamics of the strong coupling. But I mean, this is an extremely hard problem, and I mean, that's one of the reasons why it's very hard to do anything. And I mean, also the original example of the ADS-CFT corresponds with the D3 branes and so on. I spent a lot of time explaining this because if we are in this framework of string theory, we have a lot of control and there's all these symmetries and so on. And then we have many tools that help us. And if we have that many tools that help us, then we can make very definite statements. But of course, in the original version, it's at the price of being in some very academical mathematical construction, which is very far away from actually describing real physics in the real world. But okay, I mean, you know, we should be modest and have a starting point where we can do something. And then string theory helps us a lot to make concrete statements. And then we can really, at least at the theoretical level, map theories to each other and really understand what we mean by duality and so on. So I would definitely say in the last 25 years, there has been a tremendous amount of progress in the theoretical physics by exploiting these dualities and really helping, you know, find consistency conditions and understanding what's happening, you know, in these stringy brane type models on the one hand side and in these strongly coupled systems on the other side. But I mean, of course, it's true that, I mean, we are far from being done. And I mean, understanding duality itself is complicated and understanding these strongly coupled systems is complicated. And this way, this will keep us busy quite some more time to really answer your question. And okay, so I think at the moment we should be happy that we have these beautiful examples, which are really striking that completely different things are, you know, are the same, and that's certainly giving a lot of insight. But I mean, I agree that these are only a very few examples, but there's really technical obstacles of finding more of them. But that's what we're doing. I mean, this is my research, is to find more examples where we can make meaningful statements. Yeah.